what's it like to be a cellular automata in the way that's equivalent to what is it like to be a conscious human
Hmm.
being? How do you approach that? So is it looking at some subset of the cellular automata, asking questions of that subset, like how the world is perceived, how
Yeah, it's
you
something like
as that subset, like for that
yeah,
local pocket of computation, what are you able to say about the broader cellular
something
automata?
like that.
And that somehow then can give you a sense of how to step outside of that cellular
Right,
automata.
but the tricky part is that that little subset, it's what it's doing is it has a view of itself. And the question is, how do you get inside it? It's like, when we with humans, right? It's like we can't get inside each other's consciousness.
Mm-hmm.
That doesn't really, that doesn't really even make sense. It's like there is an experience that somebody is having, but you can perceive things from the outside, but sort of getting inside it doesn't quite make sense. And for me, these sort of philosophical issues, and this one I have not untangled. So let's be
Sure.
the for me, the thing that has been really interesting in thinking through some of these things is, when it comes to questions about consciousness or whatever else, it's like when I can run a program and actually see pictures and, make things concrete, I have a much better chance to understand what's going on than when I'm just trying to reason about things in a very abstract way.
Yeah, but there may be a way to map the program to your conscious experience. So, for example, when you play a video game, you do a first-person shooter.
Mm-hmm.
You walk around inside this entity.
Yep.
It's a very different thing than watching this entity. So, if you can somehow connect
right.
more and more, connect this full conscious experience to the subset of the cellular automata.
Yeah, it's something like that. But the difference in the first-person shooter thing is there's still your brain and your memory is still remembering. You still have. It's hard to. I mean, again, what one's going to get, one is not going to actually be able to be the cellular automaton. One's going to be able to watch what the cellular automaton does. But this is the frustrating thing that I'm trying to understand. How to think about being it, so to speak.
Okay, so like in virtual reality, there's a concept of immersion, like with anything, with video game, with books,
Mm-hmm.
there's a concept of immersion. It feels like over time, if the virtual reality experience is well done, and maybe in the future it'll be extremely well done, the immersion leads you to feel like you mentioned memories. You forget that you even ever existed outside that experience.
Yeah.
It's so immersive. I mean, you could argue sort of mathematically that you can never truly become immersed, but maybe you can. I mean,
Well, yeah. I mean,
why can't you merge with the cellular automata?
Yeah,
Like,
right.
I mean, aren't you
yes.
just part of the same fabric? Why can't you just like?
Well, that's a good question. I mean, so let's imagine the following scenario. Let's
Then
imagine.
can you return?
What's that? Well,
but then can you return back?
Well, yeah, right. I mean, it's like, let's imagine you've uploaded, your brain is scanned, you've got every synapse, mapped out. You upload everything about you, the brain simulator, you upload the brain simulator, and the brain simulator is basically, some glorified cellular automaton.
Mm-hmm.
And then you say, well, now we've got an answer to what does it feel like to be a cellular automaton? It feels just like it felt to be ordinary you, because they're both computational systems and they're both, operating in the same way. So in a sense, but I think there's somehow more to it, because in that sense, when you're just making a brain simulator, it's just, we're just saying there's another version of our consciousness. The question that we're asking is, if we tease away from our consciousness and get to something that is different, how do we make a bridge to understanding what's going on there? Mm-hmm. And, there's a way of thinking about this. Okay, so this is coming on to sort of questions about the existence of the universe and so on. Mm-hmm. But one of the things is there's this notion that we have of rulal space. Mm-hmm. So we have this idea of there's physical space, which is, something you can move around in that's associated with the extent of the spatial hypergraph. Then there's what we call branchial space, the space of quantum branches. So in this thing we call the multi-way graph of all of this sort of branching histories, mm-hmm. there's this idea of a kind of space where instead of moving around in physical space, you're moving from history to history, so to speak, mm-hmm. from one possible history to another possible history. And that's kind of a different kind of space. That is the space in which quantum mechanics plays out. Mm-hmm. Quantum mechanics, like, for example, something like I think we're slowly understanding things like destructive interference in quantum mechanics. That what's happening is branchial space is associated with phase in quantum mechanics. And what's happening is the two photons that are supposed to be interfering and destructively interfering are winding up at different ends of branchial space. And so us, as these poor observers that have branching brains, that are trying to conflate together these different threads of history and say, we've really got a consistent story that we're telling here. We're really knitting together these threads of history. By the time the two photons wound up at opposite ends of branchial space, we just can't knit them together to tell a consistent story. So for us, that's sort of the analog of destructive interference.
Got it. And then there's rulal space too, which is the space of rules.
Yes, well, that's another level up. So there's the question. Actually, I do want to mention one thing because it's something I've realized in recent times, and I think it's really, really kind of cool, which is about time dilation and relativity, and it kind of helps to understand. It's something that kind of helps in understanding what's going on. So, according to relativity, if you have a clock, it's ticking at a certain rate. You send it in a spacecraft that's going at some significant fraction of the speed of light. To you as an observer at rest, that clock that's in the spacecraft will seem to be ticking much more slowly. And so, in other words, it's kind of like the twin who goes off to Alpha Centauri and goes very fast will age much less than the twin who's on Earth that is just hanging out where they're hanging out. Okay, why does that happen? Okay, so it has to do with what motion is. So in our models of physics, what is motion? Well, when you move from somewhere to somewhere, you're having to sort of recreate yourself at a different place in space. Mm-hmm. When you exist at a particular place and you just evolve with time, you're updating yourself. You're following these rules to update what happens. Well, so the question is, when you have a certain amount of computation in you, so to speak, when there's a certain amount, you're computing, the universe is computing at a certain rate. You can either use that computation to work out, sitting still where you are, what's going to happen successively in time, or you can use that computation to recreate yourself as you move around the universe. Mm-hmm. And so time dilation ends up being, it's really cool actually that this is explainable in a way that isn't just imagine the mathematics of relativity. Mm-hmm. But that time dilation is a story of the fact that as you kind of are recreating yourself as you move, you are using up some of your computation. And so you don't have as much computation left over to actually work out what happens progressively with time. Mm. So that means that time is running more slowly for you because it is you're using up your computation. Your clock can't tick as quickly because every tick of the clock is using up some computation, but you already used that computation up on moving at half the speed of light or something. And so that's why time dilation happens. And so you can start. So it's kind of interesting that one can sort of get an intuition about something like that because it has seemed like just a mathematical fact about the mathematics of special relativity and so on.
Well, for me, it's a little bit confusing what the you in that picture is because you're using up computation.
Okay, so we're simply saying the entity is updating itself according to the way that the universe updates itself. Mm-hmm. And the question is, those updates, let's imagine the U as a clock, mm-hmm. Okay? And the clock is, there's all these little updates, the hypergraph, and a sequence of updates cause the pendulum to swing back the other way and then swinging back and forth, okay? And all of those updates are contributing to the motion of the pendulum going back and forth or the little oscillator moving, whatever it is, okay? But then the alternative is that's sort of situation one where the thing is at rest. Situation two, where it's kind of moving, the what's happening is it is having to recreate itself at every moment. Mm-hmm. The thing is going to have to do the computations to be able to sort of recreate itself at a different position in space. And that's kind of the intuition behind. So it's either going to spend its computation recreating itself at a different position in space, or it's going to spend its computation doing the doing the updating of the ticking of the clock, so to speak. Mm-hmm.
So the more updating is doing, the less the ticking of the clock update is doing.
That's right. The more it's having to update because of motion,
yeah,
the less it can update the clock. So that's I mean, obviously there's a sort of mathematical version of it that relates to how it actually works in relativity, but that's kind of, to me, that was sort of exciting to me, that it's possible to have a really mechanically explainable story there that isn't and it's similarly in quantum mechanics, this notion of branching brains perceiving branching universes, to me that's getting towards a sort of mechanically explainable version of what happens in quantum mechanics, even though it's a little bit mind-bending to see, these things about under what circumstances can you successfully knit together those different threads of history, and when do things sort of escape, and those kinds of things. But the thing about this physical space, the main sort of big theory is general relativity, the theory of gravity, and that tells you how things move in physical space. In branchial space, the big theory is the Feynman path integral, which it turns out tells you essentially how things move in the space of quantum phases. So it's kind of like motion in branchial space. And it's kind of a fun thing to start thinking about all these things that we know in physical space, like event horizons and black holes and so on. What are the analogous things in branchial space? For example, the speed of light. What's the analog of the speed of light in branchial space? It's the maximum speed of quantum entanglement. So the speed of light is a flash bulb goes off here. What's the maximum rate at which the effect of that flash bulb is detectable moving away in space? So similarly, in branchial space, something happens, and the question is, how far in this branchial space, in the space of quantum states, how far away can that get within a certain period of time? Mm-hmm. And so there's this notion of a maximum entanglement speed, and that might be observable. That's the thing we've been sort of poking at, is might there be a way to observe it even in some atomic physics kind of situation? Because one of the things that's weird in quantum mechanics is when we study quantum mechanics, we mostly study it in terms of small numbers of particles. This electron does this thing on an ion trap does that, and so on. But when we deal with large numbers of particles, kind of all bets are off. It's kind of too complicated to deal with quantum mechanics. And so what ends up happening is, so this question about maximum entanglement speed and things like that may actually play in one of these, in the sort of story of many-body quantum mechanics, and even have some suspicions about things that might happen even in, one of the things I realized I'd never understood, and it's kind of embarrassing, but I think I now understand a little better, is when you have chemistry and you have quantum mechanics, it's like, well, there's two carbon atoms, there's this molecule, and we do a reaction, and we draw a diagram, and we say this carbon atom ends up in this place. And it's like, but wait a minute. In quantum mechanics, nothing ends up in a definite place. There's always just some wave function for this to happen. How can it be the case that we can draw these reasonable, it just ended up in this place? Mm-hmm. And you have to kind of say, well, the environment of the molecule effectively made a bunch of measurements on the molecule to keep it kind of classical. And that's a story that has to do with this whole thing about measurements have to do with this idea of, can we conclude that something definite happened? Because in quantum mechanics, the intrinsic quantum mechanics, the mathematics of quantum mechanics is all about, they're just these amplitudes for different things to happen. Mm-hmm. Then there's this thing of, and then we make a measurement and we conclude that something definite happened. Mm-hmm. And that has to do with this thing, I think, about sort of about knitting together these different threads of history and saying, this is now something where we can definitively say something definite happened. In the traditional theory of quantum mechanics, it's just like, after you've done all this amplitude computation, then this big hammer comes down and you do a measurement and it's all over. Mm-hmm. And that's been very confusing. For example, in quantum computing, it's been a very confusing thing because when you say, in quantum computing, the basic idea is you're going to use all these separate threads of computation, so to speak, to do all the different parts of, try these different factors for an integer or something like this. And it looks like you can do a lot because you've got all these different threads going on. But then you have to say, well, at the end of it, you've got all these threads and every thread came up with a definite answer, mm-hmm. but we got to conflate those together to figure out a definite thing that we humans can take away from it, so the computer actually produced this output.